This work I have not done alone, along the list of people I must credit. Many helped to write the paper, and some of them even read it. So what's the story with Fornax A, a nearby radio galaxy? At 1500 megahertz, this is what you see. One of the brightest southern sources, seen here with the VLA. You can't help but to observe it with the Murchison-Whitefield array. Built from metal spiders, from all transmitters it is far. From the radio-quiet desert, we try to measure the EUR. We choose the emptiest spots to point, and for hours and hours we stare, but there are always pesky foregrounds, like Fornax A, which is there. So what can I do with these data on this galaxy that gets in the way? I had a look at the literature to see what others had to say. Toshiro had looked at the X-rays, only the western lobe they could see. Combining this with archival radio, they modelled the SED. Implicit in their analysis was the assumption that east and west had the same spectral index. So this is what we would test. So here's the NWA image. It's not a mystery why. You don't see just that big old blob, but a huge chunk of the sky. Now we're interested in Fornax A, so on that let's zoom in. It does look kind of blurry. The resolution's 3 out min. Now if this was television, it would be clear how to advance. Just take this radio picture and tell them to enhance. Of course we cannot do this, so instead we must degrade the VLA image resolution for a comparison to be made. Out in the lobes, the contours, they seem to line up pretty well, so the spectral index doesn't vary too much that we can tell. To investigate more deeply, we trial a range of indices, subtracting high and low frequency images with spectral tomography. Ignoring the Corin bridge, which there is no time to discuss, the lobe indices are similar, so that's good news for us. Because when we look with Fermi, we only see one blob, so we treat it as a point source, and that's good enough to do the job. From Fermi data, Rishi found the high energy SED, Fornax A appears up to 5000 MeV. We also looked in the microwave from Planck and WMAP, flux densities we did obtain for this Marcos, I think. So we put it all together to see if we could figure out how these gamma rays are produced and what the physics was about. It turns out it's not too simple. Different models, we showed 3. It's tough to fit the data, as you will shortly see. In model 1, it is assumed that the gamma rays detected are from really fast electrons whose paths have intersected with the most abundant photons that fill up all of space. The cosmic microwave background gets scattered all over the place. The electrons hit the photons and boost them up all right. This also happens to the extragalactic background line. But when we try to fit the spectrum, knowing the synchrotron quite well, we overpredict the X-rays, sending this theory down to hell. The inverse Compton model can be made to fit with a lower energy cutoff than on the line the X-rays sit. But we know the X-ray spectrum and the model's got it wrong. So we need something else, and that's where protons come along. When relativistic protons and thermal ones collide, neutral pions are created and more stuff on the side. These mesons do not last long, they quickly will decay, and this will give us what we want, many a gamma ray. So now, the data, it all fits. But it's not all good news. The total energy is way too high, so was this all a ruse? Well, we think there's a solution if the collisions are restricted to the filaments that the VLA image has depicted. If in stronger fields and denser gas these protons they do lurk, you may resolve the energy problem, but we leave this for future work. So I'll leave you with my summary, and thank you for your time. I'm happy to take questions, but only if they want.